Hello everybody. This video is us doing an example together, a guided example, graphing a function of cosecant where we're going all out and we're applying all different transformations. So you'll see we have manipulated A, B, H, and K. We have a negative vertical reflection, 1/2 vertical compression, 4/3 bigger than 1. So that's actually a horizontal compression because it's in the bonker house, plus pi over 6, bonker backward house, that moves it left, pi over 6, minus 5, down 5. So we know what everything does, but now how do we put it on paper? Well, let's see. When we graph cosecant, as you saw in the lesson video, we have that little reminder that what you're going to have to think of is what does sine look like, whether positive or negative. And then from there, we're going to create cosecant. So it's like sine or negative sine is like the skeleton of cosecant or negative cosecant. So positive sine, I'm not going to go super in depth with this little sketch. Positive sine, I'm not going to connect it. I'm going to draw it dotted, okay? It's sort of like that. Ugly dots, sorry. And then negative sine was 1, 2, 3, 4, 5 points right there. I'm just going to draw that little dotted as well. So there's either sine or negative sine. Then we dealt with the whole reciprocal process to get cosecant on there. So now y equals cosecant x, y equals negative cosecant x. So we didn't talk about the negative one in the lesson, but that's okay. The zeros of sine, those are on the sinusoidal axis. Well, what's the reciprocal of 0? Even if it's not 0, even if we move it down 5, it's still going to be treated as a 0, okay? The reciprocal of 0 is undefined. And the way you show undefined in a graph is you mark it off and say, you can't go here. Undefined, not allowed, you can't go here. So all zeros, when you change into the reciprocal, which is cosecant, all zeros are going to become what we call a vertical asymptote. All right, you might remember vertical or horizontal asymptotes from Algebra 2 when you did things such as exponential functions, logarithmic functions, rational reciprocal functions. I mean, they even happen 1 over x. That was a reciprocal of x. X equals 0 at the origin, 0, 0. And the reciprocal had a vertical asymptote at 0. And then it moved left or right accordingly. Then, next 2 steps, the max and mins, those are the only points we keep. All the other points are going to kind of change up where they are. What happens to them? Instead of it being like this with numbers that are less than 1, with it becoming a reciprocal, the numbers become greater than 1. And vice versa, flip over here. So you get these little like U-shaped graphs. And like I explained in the other recording, we don't call them really a parabola because parabolic curves have a specific shape. So, I mean, it's the cosecant graph. If you call it a U-shaped graph or a little scoop, whatever you want to call it, then you're good to go. So that's further explained if you need. That's going to go back and look at the lesson for cosecant parent function, but that's just the general shape of cosecant. Now let's apply that to this. The strategy for graphing a cosecant is you graph sine, pretend it's sine, make believe, graph sine but dotted, and then we just do a little flipperoo. That's it. Not flip like a vertical reflection, but a reciprocal flip. It's a little different. So what I'm going to do first is I'm going to, now with the sine, I was drawing the shape in first. I'm going to go ahead and draw in my sinusoidal axis first so I kind of mark myself, like where's the middle from the top to the bottom, where's the middle of my graph. So I'm just going to go here. I'm just going to put a blue dashed line for my sinusoidal axis showing the midline going all the way across, okay? That's going to be y equals negative 5. Then, so we put y equals negative 5, then we are going to, okay, we're going to put on our dotted sine wave, but it's negative, so I'm going to follow this pattern here on this picture. So I'm going to put a mark there. I'm not really going to put the dot so heavy because it's not really going to be a point on my graph. I got another tick mark. The tick marks don't represent the x-axis. It's just for my spacing. So I'm going to have down a bit, then back here, up, and then I'm back over here. This beginning, middle, and end are going to be my vertical asymptotes. I'll go over it in color later. So we're just drawing in the actual sketch of the graph, and then we'll label everything. And then instead of actually having a sine wave, we're graphing the reciprocal. So it's a special type of reciprocal. So we're going to sketch that in dashed. Beautiful, amazing. Now cosecant then, remember, you don't touch a vertical asymptote. You don't actually hit it. You get really close to it. It's like magnetic. So it's like up against the vertical asymptote, very, very close, never, never touches. Horizontal asymptotes, on the other hand, those are more about end behavior than they are about restrictions and being undefined. So you want to make sure with the horizontal, a vertical, or really asymptotes in general, like why are they there? Where did they come from? Can you cross it? Can you definitely not cross it? This case, we cannot cross it. So what is also done, we took care of the negative because we had that negative shape, and we took care of the cosecant because we graphed what cosecant would look like in this situation. Now, what do we usually do next? Next thing that we usually do, we have A, B, H, and K. Usually, I think we would deal with the A, right? Kind of start on the outside and work our way in. So the A value of -1/2. That was the amplitude when we graphed sine and cosine, which was this guy right over here, okay? And it really still is that measurement. So it's affecting that skeletal sine wave. So this is going to be 1 unit, or not 1 unit, 1/2 a unit below the blue dashed sinusoidal axis. And this is going to be 1/2 a unit above the blue dashed sinusoidal axis. It's not quite amplitude in the same way, but you know, still has that same impact on the graph. So that'll be 1/2 away, 1/2 away. So we could kind of throw some more numbers out there where we can kind of mention if that's -5, what would that be up there? That's going to be negative, careful with the negatives, 4.5. And then this one is -5.5. So it shouldn't feel too crazy yet, right? It's still very similar. I'm just going to reinforce the negative. Whenever I do this with a dashed line, I feel like I lose my negative sign. So it like blends into the dash. Next thing that I usually look at is the plus or minus h. What's the h value? So this is plus pi over 6. Bunker house. So it's going to go left pi over 6. That is this spot. Now this would have maybe been a dashed mark whether it was an asymptote or not. It just happens to be an asymptote as well. So that right there is my h value. What else can I put on here? We can put on, all right, these are all negative. I can draw my x-axis above them. A lot of times we have all positive, so we put our y-axis or x-axis below. But in this case, my x-axis will be above because I have negative numbers. So we'll just fake it right here. I'm just going to draw my x-axis. There we go. And when I draw my y-axis, I'll put a little zigzaggy break because 4.5 is pretty close, and then to scale it makes no sense. It's all fine. 5 tick marks we're going to need. Where are they? 1 right there. Another. That's 2, 3, 4, and 5. There's my 5 tick marks. That one is -pi over 6. And we could do, I'm going to write it above. Think ahead equals, leaving that equals, why? Because we might have to find a common denominator, okay? So we might want to label it again with that common denominator. That's done. Last thing that we have to deal with is the 4/3, right? 4/3 is my B value. It will affect the period. And then after it affects the period, of course, it will affect the quarter period. And that will tell us, boom, 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 how far apart each of the tick marks are, and therefore how much we have to keep adding each step of the way. So where can I squeeze this? Let's see. The period formula is still, it goes with sine, 2 pi over b. b is 4/3. Don't panic. I know people don't like fractions, but it's not a big deal. Period equals 2 pi over, I'm going to put it in parentheses, 4/3 equals, that just becomes 2 pi times 3 over 4. Think smarter, not harder, reduce first. Think smarter, not harder, reduce first. So the 2 and the 4 become a 1 and a 2. 1 pi times 3 over 2. The period is 3 pi over 2. That's the period. Now we need what is 1/4 of that. So the quarter period, Q, is 1/4 of the period. Then that becomes 3 pi over 8. So that means I need to find the common denominator between these two, because I'm going to have to do negative pi over 6 plus 3 pi over 8 to get to this spot. I'll put the answer up top, but I'll put a little note. Negative pi over 6 plus 3 pi over 8, but we don't have a common denominator. What would the least common denominator be between 6 and 8? Some people are just going to multiply this on top and bottom by 8 and this on top and bottom by 6. But you're not using the least common denominator. When you do that, you're using a common denominator. The thing that sucks, your numbers are pretty big. So again, for that breakdown of how to deal with a common denominator, I have one bottom of 6, the other bottom is 8. Imagine the prime factorization. 6 is 2 times 3. 8, I'm not going to do many steps in this tree. It's 2, 2, 2. Now, they're crying and jealous of what the other person has. This one is crying because it wants a 3, top and bottom by 3. This one's crying because this one has 3 2s and they only have 1. So, top and bottom by 2 more 2s or a 4. If you look at all the denominators now, they're 2 times 2 times 2 times 3, both of them. So what is the least common denominator? Whatever that becomes, and that's 24. So if you just gave this a 6 on top and bottom and this an 8 on top and bottom, you would be using 48. So we're going to use 24. So that all being said, that's the real process. You don't have to really necessarily do that. You could kind of do it in your head. So this I'm going to multiply on top and bottom by 4. Gives me a 24, and this one on top and bottom by 3. That's negative 4 pi over 24, what's really happening, plus the quarter, which is 9 pi over 24. So if that's negative 4 pi over 24, my first tick mark, that next one is where I'm going to add that. What's negative 4 plus 9? 5 pi over 24. So that's this tick mark right here. Well, the other nice thing is I've already moved from negative to positive, so what can I draw? I could draw my y-axis. So there we go, y-axis. I mentioned we're going to do a little squiggle guy, a little break. Then I'm going to mark this, negative 4.5. This is negative 5, and right about here, negative 5.5. So my y-axis is done, and now I just gotta add 9 to my numerator 3 more times, and you're done. That's it. That's it. Nothing crazy, okay? 5 plus 9, what do we get? 14? Am I right? I think so. 14 pi, sometimes, brain fart, over 24. I know it reduces. You don't have to do that. Don't create more work for yourself. It's easier in the long run if you leave it alone. You'll see why when we do domain. After that, add 9 more. 9 pi over 24 again. 14 plus 9, so we get 23 pi over 24. One more time for this spot right there. 23 plus 9 is 32. So 32 pi over 24. And that is the label for that tick mark right there. If you ever want to check, sorry, that 24 is There we go. If you ever want to check if your answer is correct, one thing you can do is you can just subtract your last minus first and you should equal the period. So in this case, 32 pi over 24 minus negative 4 pi over 24. Minus a negative, well, that's plus. 32 plus 4 is 36. 36 pi, sorry, I'm squeezing, over 24 reduces by, I believe, 6 is the biggest, maybe? 12, silly. 12, 3 pi over 2. And what do we get for the period before? 3 pi over 2. Winner, winner, chicken dinner. So I hope that this was not too terrible for people. If you feel pretty decent about it, let me go in and put my asymptotes though. I'm gonna draw them in, I don't know, green. So the pink, I was always putting pink for that first spot, no matter what. So I'm gonna do my asymptotes, I guess, in green. I'll try to remember. There's our graph. And like I said, we're gonna do domain and range in a separate video. And before you go, let's give you one to do on your own. And this will be your assignment to try to show yourself that you know what you're doing. Let's do, let's spice it up a little bit. 2/3 cosecant. Ooh, I have a fun idea, but I'm a little scared. Let's do, 4x. I'm going to try, it's going to be like a light version of something that can be very, very, very confusing. Plus 4 pi over 5 close plus you know, I don't like to repeat a digit, so let's do 8. Okay, so this is one I want you to do on your own. However, what did I do differently? Can anybody see what we, oh, and the title still says parent function. That's so sad. You guys have to tell me when the title is wrong. Graphing cosecant with transformations. Does anybody see what's different about this than every other example we've done so far? No one wants to speak up, volunteer.
Maybe.
The B is a 4, but do you see that we're missing a parenthesis?
Yes.
So the 4, you have to kind of factor out the 4 because there's a 4 here and a here. This one's easy. They're not always going to be this easy. You're going to factor out the 4 before you graph it. So you're going to do y equals 2/3 cosecant 4 something plus 8. So you're going to have to fix what's in here before you graph it. Okay? So this is your example to do on your own. And I'm wishing you luck. I set you up over there with that, but you should be more than fine. Okay? So if you feel like you are doing pretty good and you're pleased with your level of understanding, give yourself a high five, give the video a thumbs up. If you are not pleased, if you're insecure, you're not confident, you are sad, you are scared, then put a thumbs down, okay? Hope it was helpful and have a good day.